Hello. In this video, we're going to go and take the graphs that we filled in a table of value for in our previous video and actually graph them. And remember, the idea is that we're talking about this thing called a parent function or parent relationship or parent graph. In our case, it's y equals x squared. And we want to see how we can apply some set of rules to graph relationships that are similar, relationships that share the same parent operation. So that is squared. So this is actually my second time making this video, so this writing here I wrote previously, but I'll leave it up. So what we're really looking at here is we're looking at this type of situation. If we have y equals x minus k squared, the k value is thought of as a horizontal shift, k units right. And so one thing we recognize is that on this graph, if I see minus, I think typically to the left. However, in the previous video, we established that minus is a shift to the right. So what we often say is we say that horizontal shifts lie. And in fact, the same thing applies with stretches in a slightly different manner, though we're not going to look at horizontal stretches this year. So with horizontal shifts, we know that if it's a minus, it's shifted to the right, and if it's a plus, it's shifted to the left. Again, we always like to think of bigger ideas. We teach this concept, and then what happens is students get to grade 11 and they learn a variety of other types of relationships. The bigger idea is that if you add or subtract from x before the parent operation, you apply a horizontal shift. So here, the parent operation is squared. We have to minus k before we square the value, so we think of this minus k as a horizontal shift. It just happens that all our examples have a parent operation of squared because we know what the parent graph y equals x squared looks like. We can very easily shift everything appropriately. So I've already graphed y equals x squared here in green. If I was to graph y equals x minus 2 squared, I wouldn't need a table of values. I would just take each x value and shift it 2 to the right. So we see 1, 2, there's my new vertex, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And so there's the graph of y equals x minus 2 squared, drawn based on an understanding of how I shift my parent graph to this new relationship, what we call a child graph. A nice observation to make is that there's been no change in the shape of this graph. It has the same shape. So if we recognize that it has the same shape, what some people will do, another way to apply this is they'll say, well, let's do this one, y equals x plus 5 squared. Well, we know the vertex is going to be shifted 5 units to the left now. So there it is. And since the shape isn't changed, I can kind of walk out the same shape. Over 1, up 1, over 2, up 4, over 1, 2, 3, up 9. Over 1, up 1, over 2, up 4, over 3, up 9. And then I just kind of connect the dots like this. So again, back to the bigger idea that I was talking about here is, even though we don't know what a y equals x cubed graph looks like, we can recognize that since we're subtracting a value before we cube it, this would apply a horizontal shift 2 units to the right. We just have to know what y equals x cubed looks like, which we could probably figure out. Now let's do this last graph here. Let's do this one in red. So this one, it has two things happening. With y equals minus x minus 3 squared, there's two things happening. We have what I said, two transformations. Okay, really key point here, shifts last. When you're writing out your transformations, always think of your shifts last. Okay, so the first thing we see is since a is negative, we have what's called a reflection across the x-axis. So that's what we say we're doing, but what we do mathematically is we multiply y by -1, because we're going to take each y value and multiply it by -1. The second thing we do is we have -3, so we shift 3 units, and since it's minus, it's going to be to the right. So what we say now is we say add 3 to all x values. Again, this is the first time I've actually written it out in this way, but I like to take a second and think about my transformations in two forms. I think about it in terms of what is it doing in words, and what does it do mathematically to each point. So with this one, we have a -a value, so that's a reflection across the x-axis, which means we multiply all the y values by -1. We also have a -3 here, and that's a shift 3 units right. So that means we add 3 units to all the x values. So if I start at my parent graph here, I'm going to say we're going to multiply the y by -1, so it stays the same, and then we go 1, 2, 3. There it is. Let's take this point 1, 1. So we're going to put it in the negative, 1, -1, and then go 1, 2, 3. Into the negative, that's multiplied by -1, 1, 2, 3. So if we have 2, 4, that's going to become 2, -4, 3, 4, 5. If we have -2, 4, we're going to have -2, -4, and then we have -1, 0, 1. And the last point's not going to fit on the graph, so I can just leave that out. And there's my graph. And again, all sorts of little checks you can do to see that you've done this right. There's my axis of symmetry, and wonderfully that symmetrical behavior is occurring. So that's a distance of 2 and 2. That's the distance of 1 and 1. That's a little mental check you can do. So what we've seen is that when we add or subtract a value to the x before we square it, we think of that as a horizontal shift. The bigger idea is that this same idea of a horizontal shift applies to a wide variety of relationships, many of which you'll learn in your future math courses, but it's nice to make that connection now. So all we have to kind of identify is, do we add or subtract to x before the parent operation? In our case, the parent operation is always squared, but the parent operation could be something like a cubed, could be a square root, lots of different variations for us to look at. Hope that helped.